Welcome back to Tech 293. Today is Thursday, January 21st. Today I'm going to make two different videos, but before we do that, let's take a look at the schedule. So if I look at today's row on the schedule, I see that Quiz 2 is due on January 24th. That's this Sunday at 11:55 p.m. Quiz 2 is going to cover material up through and including today's material, which includes material on lattice structures and grains in materials. So don't forget about that, Quiz 2. You can take it as soon as you're done watching this video. Of course, you can use the video if you want to. You can use the lab manual. You can use anything you want except each other to complete Quiz 2. So don't forget about that. Again, Quiz 2 due Sunday, this Sunday by 11:55 p.m. Also, we have Lab 1 due coming up. Lab 1 is due on January 26th. That would be next Tuesday. Once again, that's due by 11:55 p.m. next Tuesday. All right, and you can submit that on RegNet under the Assignments tab on RegNet. All right, so that's the announcements with regards to the schedule. With regards to the videos today, I'm going to make two different videos. The first is going to be a continuation of materials science that we started talking about in the last class. In today's session, we're going to talk about lattice structures and grains. So I have a few things to show you. First of all, I have some models like this, and you can see another one back there. I have a couple more too. So this is a model of a unit cell of a lattice structure. So this is the simplest repeated unit that you have inside of a crystalline lattice structure. And there are lots of materials that have crystalline lattice structures. So you can imagine something exactly like this, repeated in all different dimensions, stacked next to each other, stacked on top of each other, thousands to millions of them stacked in every dimension. That would form a 3D crystalline lattice structure. And when you zero in on that and you simplify it down to the simplest repeated structure in that specimen, the simplest repeated structure is something like this. This is a unit cell for one particular type of lattice structure. And we're going to talk about several different types of lattice structures that appear in nature today in today's first video. I've also got actually a song that I'm going to play you. That's kind of unusual. I won't play you very many songs in this class, but I do have one for you today. Also, I have a video within a video that I'm going to show you about grain formation and grain structures within specimens. All right, so that's going to be the first video today. And in the second video today, we're going to talk about Lab 2. So we're going to go through the instructions for Lab 2, and we'll talk through them and make sure we're all clear on them. That way, when we actually go to do Lab 2, or when you watch the video of me doing Lab 2, you'll understand what we're doing and why we're doing it. And it'll hopefully make sense to you as we're doing Lab 2. So that's what we're going to do today in the second video. So let's go ahead and get started by talking about lattice structures. All right, this is kind of day 2 of the materials science section in this class that I've referred to a couple of times. So we know that ionic and covalent and metallic materials can all form lattice structures. It's most likely to occur in ionic bonded solids and in metals. All right, and the type of lattice structure they form, we're going to talk about 14 different types of lattice structures. Not in great detail. There are only 4 of them that we're going to talk about in any level of detail. You'll see those in just a minute. But which type of lattice they form depends on a bunch of factors. It depends on what material it is, and factors like what's its size of the atom and how electronegative it is. Also, believe it or not, temperature has an effect. And if I have a material, there are some materials where if I heat it up to a higher temperature, it actually changes what type of lattice structure it's going to form. The most common example of this is actually iron or steel, since steel is mostly made of iron. And we'll talk a lot more about that in about 2 months from now. Pressure can also have an impact. and the alloying materials, in other words, the impurities that you mix in with it. Mix-ins, the word mix-ins reminds me of Cold Stone ice cream, because you go through the line and you ask for mix-ins like Reese's peanut butter cup pieces or Reese's pieces, and they mix it into the ice cream. Well, alloys are kind of like that. You've got mix-ins that you mix in with the base material, and it has desirable results, usually. That's why you do it, to the resulting alloy material. So we'll talk a little bit more about alloys actually later today. In the lattice structures, there are 14 basic types of lattice structures, and they're called the Bravais lattices. You can see how it's spelled down here, B-R-A-V-A-I-S, Bravais lattices. And here are the 14 basic types of Bravais lattice structures. The good news is that I am not going to ask you to memorize the differences between all 14 of these. I want you to know that there are 14, and I want you to know some details about the 4 most common ones. And the 4 most common ones that I want you to know about are the simple cubic, the face-centered cubic, the body-centered cubic, and the hexagonal, often called hexagonal close-packed, HCP. We'll talk more about that in the next couple of slides. But let's see. I think I can tell you the differences between all 14 of these, if I can remember all these. So the way we define these lattice structures is by the 3 side lengths. So each of these has 3 characteristic side lengths, A, B, and C. We call them A, B, and C. So this might be A, and this might be B, and this might be C. And each lattice structure has 3 characteristic angles, and they're usually called alpha, beta, and gamma, the first 3 letters in the Greek alphabet. So for this basic one, this might be alpha, this angle, this might be beta, and this might be gamma. All right, so for these cubic ones, they're just cubes. They're plain old cubes. So A equals B equals C. The side lengths are all the same, and all of the angles are 90 degrees. So they're just like a basic cube. The hexagonal one of the side lengths, this one, is different, and one of the angles, this one right here, is not 90 degrees. Then the tetragonal ones, which are less common. The rest of these are less common, a lot less common. But the tetragonal ones, we have one side length that's not equal, but all the angles equal 90. In the orthorhombic, that's these 4 down here, none of the side lengths are equal. A does not equal B, does not equal C, but all the angles equal 90. In the rhombohedral one down here, all the side lengths are the same, but none of the angles equal 90 degrees, so it's all kind of tilted. And then in the monoclinic ones, these are kind of weird. 2 of the angles equal 90 degrees. That would be the way. It's funny the way we're looking at it, but this angle up here is 90, and this angle over here would be 90, and this one would not. So 2 of the angles are 90, but one's not, and none of the side lengths are the same. And then triclinic's actually easy. That's the one that's all jacked up. It has no angles equal to 90 degrees, and it has no equal side lengths. All right, so that's the basic lattice structures. Again, you don't need to remember everything that I just said, but that's basically how lattice structures are made up. That's the basic unit cells in the different types of materials that form lattice structures. And what's kind of neat to maybe help you remember these, although I don't know if it actually would help you remember these, is a song. There's a song that someone wrote about these, and I have to warn you ahead of time, it's pretty terrible. It's a pretty terrible song. I don't know if it's going to get stuck in your head or not. It might, and if it does, I apologize. But there is a song, and hey, I may as well play it for you, right? I've got it, so I may as well play it for you. And you know what? I'll go ahead and say this before I play the song. What I have done in every semester that I have taught this class, that's about 6 or 7 semesters or something like that, I have offered this, that if anyone wants to memorize this song and recite it in front of the class, don't have to sing it, just have to recite it by memory, then I will automatically give you 100% on the first exam. All right, so that is an opportunity for you if you want to guarantee yourself 100% on the first exam. All you have to do is memorize this song. Probably easier said than done. I'll talk more about how to do that after I play this song for you. But let me go ahead and play this song for you. So, and before I play the song, I'm going to share the lyrics so that you can see the lyrics. All right, so here are the lyrics. It's the Brave Lattice's song. Now let me start the music. I warned you, okay? It's terrible.
If you have to fill a volume with a structure that's repetitive, just keep your wits about you, you don't need to take a sedative. Don't freeze with indecision, there's no need for you to bust a seam. Although the options may seem endless, really there are just 14. There's cubic, orthorhombic, monoclinic, and tetragonal. There's trigonal, triclinic, and then finally hexagonal. There's only 7 families, but kindly set your mind at ease. 'Cause 4 have varieties, so there's no improprieties.
'Cause 4 have varieties, so there's no improprieties. 'Cause 4 have varieties, and there's no improprieties. 'Cause 4 have varieties, so there's no improprieties.
These 7 crystal systems form the 14 Brave lattices. They've hardly anything to do with artichokes or radishes. They're great for metals, minerals, conductors of the semi-kind. The Brave lattices describe all objects that are crystalline.
Half done.
The cubic is the most important one in my experience. It comes in simple and in base and body-centered variants. And next in line's tetragonal, it's not at all diagonal, just squished in one dimension, so it's really quite rectagonal. The orthorhombic system has one less degree of symmetry, because an extra squish ensures that A not equals B or C. If angle gamma isn't square, the side lengths give the signal. For monoclinic, if they're different, or if equal trigonal.
Of course, for trigonal, recall that no beta gamma. All our angles that are equal but don't equal 90. All angles that are equal but don't equal 90.
If you switch the lattice up in every way that is conceivable, you'll get the least amount of symmetry that is achievable. It's called triclinic, then remains the one that really self-explains. Hexagonal gives us no pains, and so we now may rest our brains.
Okay, I think I'm going to stop there. All right, so I said I'd give you some more details. If you are interested in trying to memorize this, then if you succeed in memorizing this, and you demonstrate that you have memorized it, then I will give you 100% on the first exam. That being said, I have offered this, I think, every semester that I've taught 293, 6 or 7 semesters. And guess how many people have taken me up on that offer? Yeah, a big zero. And I don't blame them. Quite honestly, I think it's probably easier just to study for the first exam and do well on the first exam than it is to memorize this song. But there's always a first. You could be the first one. So if you want to be the first one, I want to give you the same opportunity to memorize this and get 100% on your first exam that I've given previous semesters. So what I think I'll do is, if you want to memorize this and then demonstrate that you have memorized it, have someone else take a video of you and have them kind of pan around a little bit to show that there's no piece of paper that you're reading off of. What I should do is have you face the camera but close your eyes while you're reciting it, and that way it's clear that you're not just reading from something that's just beyond the camera. Okay, so if you want to take advantage of that, you can do that. Make a video, and then in previous semesters I had them, or I told them they would stand up in front of the class and recite it. There's not really a class to stand up in front of these days, so just post it on YouTube and send me the link on YouTube. And then if I watch that video and if it is clear to me that you've actually memorized it and you're not just reading something from just off the screen, then I'll give you credit for it and you'll get 100% on your first exam. All right, so that's the song. I like that song. It's kind of terrible, but kind of fun in a weird way. All right, let's go back to the slide presentation. So you should know that there are 14 Bravais lattices, and at the end of this presentation, you should know some more details about these 4: simple cubic, face-centered cubic, body-centered cubic, and hexagonal, which we're going to call hexagonal close packed. There we go. Okay, the reason I want you to know about those 4 is because those 4 are by far the most common in nature. And I can even make this table down here where I plot lots of the most common metals that we're going to work with in this class and that are just most common in engineering applications. And you can see that actually all of them are one of 3. They're either FCC, which is face-centered cubic, or HCP, which is hexagonal close packed, or BCC, which is body-centered cubic. So really, it's fair to say that the vast majority of materials are one of those 3. But simple cubic forms the basis for BCC, FCC, and HCP. So I want you to know a little bit about simple cubic as well. It's actually really uncommon. There's only 2 metals that form simple cubic lattices. One of them is one phase of molybdenum, and one is polonium. And neither one of those are very commonly seen in structures or design applications. So these 3, BCC, FCC, HCP, are by far the most common. All right, so let's talk through each one of these in a little bit more detail. Simple cubic is the most basic lattice structure, where you just got this cube with equal side lengths and all angles equal 90 degrees, and you've just got an atom on each vertex, each corner of that cube. That's it. And then you just stack them together, and in all 3 dimensions you've got a very large lattice structure, and that's all there is to that. It's not very common because it's not a very efficient way of packing them. There are actually much more efficient ways of packing things together. And nature favors efficiency. And so this is not very efficient, and so it's not very common in nature. The next one is body-centered cubic. So with this one, take your simple cubic cell, and then right in the middle of that unit cell, put another atom. All right, that's all that body-centered cubic is. And here is a good example. Normally I would pass this around the class, but you can see that if I kind of rotate it, you can see maybe a little better. So it has an atom at each vertex or each corner of the cube, and then in addition, it has one right in the middle. So this is a body-centered cubic lattice structure. I've got another one. It's made from, I think probably Tinker Toys. Is that what these were? I don't know. I never really got into Tinker Toys when I was a kid. I was big into Legos, but not so much Tinker Toys. But anyway, same idea here. You can see that it's a body-centered cubic because it has one atom at each corner, and in addition, it has one right in the middle. I don't know why this one is a different color. In reality, these would be the same atoms. So this could be, you know, for example, iron is pretty common, a material that forms a BCC lattice structure. So these would all be iron. You wouldn't necessarily usually have a different one right in the middle. It's the same as every other one on all the corners. All right, so body-centered cubic is a very common lattice structure in materials. Another one is face-centered cubic. And what this one is, take your simple cubic cell, and then on each of the 6 faces, you add another atom. And here is a model of a face-centered cubic. Kind of hard to see, probably, but you can kind of make out what's going on. So it's got an atom at each corner or vertex, and then in addition, it's got an atom on each face of the unit cell as well. There's not one in the very middle like the body-centered cubic had. There isn't one in the middle. There's just one on each face. So we call this face-centered cubic. And here's another example of a Tinker toy that has a face-centered cubic structure. So once again, I'm not really sure why whoever made this put different colored pieces on the faces, but in general, they're not. These would all be the same types of atoms in general. All right. So a good example of this would be like copper, gold, silver. Lots of these are FCC structures. And then hexagonal close packed is what we called hexagonal a couple slides ago, but HCP is normally what we call it, hexagonal close packed. And I didn't mention this before in the previous slide, but face-centered cubic and hexagonal close packed are both what we call close packed structures. They're both close packed lattice structures. And what that means is that for a given diameter of sphere, the most efficient way of packing as much volume, as many spheres as you can in a given space, the most efficient way to do that is either with FCC or HCP. They're the same. They actually have the same packing efficiency. So if you want to pack a lot of spheres into a small space, like say you want to pack as many apples as you can into a box. I'm looking at like a shipping box in my office over there. Well, if you want to ship as many apples as you can in a box, you should stack them either in an FCC organization or an HCP organization. They're both the most efficient possible. And believe it or not, it's hard to see, but actually FCC and HCP are quite similar in the way they're arranged. You wouldn't think so by looking at the unit cells, but actually they are. So if you, to kind of explain this a little bit, let's say you put down one layer of spheres, like in a ball pit or in a box or something like that, right? And then when you go to put the second layer on, you have some choices about where you're going to put those spheres. Are you going to put the next layer, are you going to put an apple or whatever right here in this little depression, or are you going to put it right here, or are you going to put it right here? you have some choices about where your next layer is going to go on top. All right, hopefully you can see that. And then with the third layer on top of that, you have some choices about which divots or depressions in the second layer you put the third layer. You can put them in an apple in this depression, or in this depression, or in this depression, or divot, you know, or whichever, whatever ones you want. So you have some choices about where to put them. So if you look at the way an FCC is constructed versus an HCP, as it happens, an HCP has an ABAB structure, whereas a cubic close packed, which is also, it's just another word for FCC. FCC, face-centered cubic, another word for that is cubic close packed. Close packed means most efficient possible. And an FCC structure has an ABC, ABC. I guess they call it ABC, and then this is another layer C down here. So what I mean by that, if you look at, say, this stack of apples and oranges over here, so here's an FCC structure, and FCC has an ABC, ABC structure. So there is a green apple on the first layer directly below this green apple right here. We can't see it, it's buried, but there is an apple, a green apple, directly below this green apple right here. There is not a green apple directly below any of the red apples, and there's not a green apple directly below any of the oranges. All right, that's what I mean by an ABC, ABC layer. Down here in the HCP structure, it has an ABAB layering structure. And so there is a red apple, probably this one right here that you can barely see, that is directly below this red apple. And similarly, there is a green apple directly below this one. It's probably right there that you can just barely see. All right. So even though the unit cells for FCC and HCP look vastly different, as it turns out, it's just about how you layer the stacks of the spheres. Okay. All right, the packing factor is a term that we use to describe how efficiently it's packed. And it's basically what percent or fraction of the available space is taken up by the spheres themselves. If I were to pack as many apples as I could into a box, what percent or fraction or decimal of the volume of that box is actually occupied by apples? Okay, that's what packing factor is. So we can do these calculations, but there's only so many different Bravais lattice structures. And so it's frankly just easier not to do the calculations every time, just memorize the packing factor. So I want you to know these packing factors. I'm not going to make you memorize the packing factors for all 14 Bravais lattice structures, but none of them, I can tell you, are better than 74%, because 74% is close packed. That is the theoretical limit to how efficient you can pack spheres. All right, so you should know that simple cubic has a packing factor of 52% or 0.52. BCC is 0.68, and both of the close packed lattices have a packing factor of 74% or 0.74. And that's as good as you can get. And the lattice structure affects the density of the material, which is probably pretty intuitive. The more you can pack into a given amount of space, the denser that material is going to be. All right, so here's a question. It's sort of rhetorical, but let's say that you are going to have a snowball fight this winter, and the question is, you want to stack up a bunch of snowballs for your inventory for ammunition, and the question is, should you stack them? Well, what lattice structure should you stack them into, right? So if you've been paying attention to the previous slides, you should probably know that Well, it doesn't matter. If it wants to be, if I want to make it efficient, then I should do it in a close packed structure. But it doesn't really matter whether it's FCC or HCP. They're both close packed. They both have a packing factor of 74%. And so it doesn't really matter. I just thought this picture was kind of funny because who would do this? Who would make snowballs and then intentionally stack them up in an FCC structure and in an HCP structure? This just seems totally ridiculous. And I have to admit, these snowballs look suspiciously spherical to me. So either these aren't real snowballs, they could be just like styrofoam balls, or it could be real snowballs, but maybe somebody had a mold that they were like using to form the snowballs. That's possible. I'm not really sure. I just found this on, I don't even remember where, social media somewhere. I don't know. So it doesn't really matter for efficiency purposes which way you're going to stack them. And here's the elf, if you've seen the movie, The Elf. This reminds me of the scene in The Elf. So he's an elf, all right? So Will Ferrell is an elf. He comes from the North Pole, and it's a humor movie, as these Will Ferrell movies usually are. And so he's an elf, and so elves are really good at snowball fights. And so this is the scene in the movie where the elf gets into a snowball fight, and he just demolishes everybody else, all the normal humans, in the snowball fight. So he's like, and he's like a rapid fire snowball throwing machine, and it's funny. All right. Okay, let's talk about deformation of lattice structures. Remember, metals form into lattice structures. So when we deform the metal, we are deforming the lattice structure. But how? Okay, so a couple times ago, was it two times ago, we talked about elastic and plastic deformation. Remember, elastic deformation, that's like what happens when I go home in the evening and I put on a pair of elastic waistband pants, right? And the waistband expands when I put them on, and then it goes back to its normal shape when I take them off. So elastic means temporary. It can expand and then go back to its normal shape. That's elastic. And remember, plastic deformation is permanent deformation. You're not going to recover that after you remove the force that you applied. So in elastic deformation, what happens is the entire lattice structure stretches. So like if I had this lattice structure, and remember this is, there are thousands in every dimension, in 3 dimensions. And if I pull on this, then the whole lattice structure kind of stretches. So just imagine that like the distance between these just gets a little bit longer as I pull on it. So I'm just stretching the whole lattice structure in that dimension. And then when I let go of it, then it goes back to its original position where it wants to be. But plastic deformation, I'm actually causing some layers, like say this layer, to slide relative to other layers, like this layer. So we call those slippage planes. Like if I did this, if I caused this plane to slide relative to this plane, then this would be a slippage plane right here. And if I did that, that would cause plastic deformation, and the lattice structure is not going to go back to its original position after I release that force. So this is a slippage plane right here. And you can see over here, this is a 2-dimensional view. You can get slippage planes in lots of different orientations. They could be horizontal or vertical or at angles. There's lots of different orientations for slippage planes. All right, yeah, so I think I just said this. Just to note that you can get deformation across multiple slippage planes at the same time. And if you do that, then you're causing plastic deformation and you're not going to recover the shape of the material. All right, now let's talk about the impact of lattice structures on the mechanical properties of the materials, because they do. FCC materials have different properties than BCC and HCP. It affects the mechanical properties of the material. All right, so there's two key considerations that we have to think about, all right, that turns out make an impact on the mechanical properties. The first one is that cubic lattice structures tend to allow slippage to occur more easily. In other words, you don't have to pull on it as hard to get plastic deformation. So if you get cubic structures, they tend to allow slippage or plastic deformation more easily than non-cubic lattice structures because of symmetry, because the cubic lattice structures have more planes of symmetry. All right, so that allows slippage to occur more easily. So think about what that means for us in our 4 basic lattice structures. Well, there's only one that wasn't cubic. That was the hexagonal. So what this first bullet point tells us is that the simple cubic and the face-centered cubic and the body-centered cubic tend to allow slippage to occur more easily because of symmetry than the hexagonal close packed. All right, so that's the first bullet point. The second bullet point tells us that close packed lattice structures, now what were those again? Those were the FCC, otherwise known as cubic close packed, and the hexagonal. Hexagonal was also close packed. So the FCC and HCP are the close packed ones, and they allow slippage to occur more easily because the slippage planes are more dense. So therefore, you've got more slippage planes per unit volume. All right. So with the two of these combined, think about what this means, the two of these combined. All right, in the first bullet point, it's telling us that, all right, simple cubic, FCC, and BCC are going to tend to allow slippage to occur more easily than a hexagonal. And in the second one, it tells us that the close packed, that's FCC and HCP, tend to allow slippage to occur more easily than the others, not close packed, all right? So that's FCC and HCP. So which one lattice structure fits both of these categories? If you think about it for a second, it was FCC. FCC, face-centered cubic, otherwise known as cubic close packed, tends to allow deformation more easily than the others because it meets both of these factors. It meets both of these. All right. So think for a second. Usually, if we were in person, I would ask you to rattle off some names of metals that you think tend to be kind of soft and not very strong. All right. So what are some metals that you could, if you had a long section of the metal that you'd be able to bend? All right. And usually people will come up with things like copper and gold and silver and platinum. Those are probably the most common ones that people come up with. And so keep those in mind: copper, gold, silver, platinum. Let me go back about 6 or 7 slides here to our table, and let's check this out. Copper, let's look for copper. Copper is right here. Hey, it's an FCC lattice structure. Gold, gold right here. Hey, it's an FCC lattice structure. Silver down here. Hey, it's an FCC lattice structure. How about platinum? Platinum's also used for jewelry a lot. Platinum is also an FCC lattice structure. So is nickel. So is lead. Oh, lead. I should have said lead. Lead's a good one. It's a soft, very dense, but soft metal. Gold, copper, aluminum. Yeah, aluminum is relatively soft and not particularly strong. So you should know this, that you should know these 2 bullet points. You should know this factor right here, that cubic lattice structures allow slippage more easily than non-cubic lattice structures, and you should know that close-packed lattice structures allow slippage more easily than non-close-packed lattice structures because of the density of the slippage planes And you should know that what that means, combining these two, is that FCC lattice structures tend to be softer and weaker than simple cubic, BCC, and HCP lattice structures. That's exactly what I just said on this slide right here. Right, and remember that simple cubic, it's the base unit cell, so I want you to know a little bit about simple cubic, but it's really uncommon in nature. Only polonium and one phase, we'll talk about phases a few months from now, but one phase of molybdenum. Okay, now we're going to talk about alloys because they fit in very well with this topic of lattices. So alloying materials are kind of like mix-ins at Cold Stone ice cream, where you mix them in and now you've got the base material and you got mix-ins that are kind of randomly distributed inside that base material. So if you look at these lattice structures, any of these, you can see that there are spaces in between here, like right here and right here and right here, and in here, in here, and in here, and in here. You can see that there are spaces or voids in the lattice structure where you could fit other atoms, especially if they're smaller atoms. But there are places where you could fit other stuff inside those lattice structures. And in this drawing down here, all the red dots are interstitial locations or interstitial sites. Interstitial kind of means in between, and it means in between the lattice structures, in between the base elements in the lattice structures. So these are 3D views. Here's a 2D view of interstitial locations. And for alloys, we can have a couple different kinds of alloys. We can have an alloy where we have a different kind of material that gets mixed into the interstitial locations. Or we could have what's called a substitutional alloy, where some other base element actually takes the place and substitutes for one of these base elements in the lattice structure. So it just substitutes for one of the main positions in the lattice structure. All right, some good examples here for interstitial alloy. A very good example is just steel. Because steel, the base element is iron, and the mix-in is carbon. And we'll talk a lot more about carbon steel in the coming months, but usually you have less than 1% carbon. Usually it's somewhere between 0 and 1% carbon. So all of these green interstitial circles, those could be carbon, and these red circles could be iron, and that would be an interstitial alloy. A substitutional alloy, a good example of that could be bronze. Bronze is copper and tin mixed together, or brass. Brass is copper and zinc mixed together. And in both of those cases, they're substitutional. So zinc can just take the place of the copper elements in this, if it's brass. And then you've got your combinations where you've got both substitutional and interstitial alloys. Probably the best example of that, most common that I can think of, is like some of the exotic steels, like chromoly steel, where it's steel, so you've got carbon mixed in, that's these green dots, and then the blue dots are the substitutional elements, and that could be chromium or molybdenum in the case of chromoly steel. All right, so I guess I skipped over this first part. What is an alloy? It's when you mix things together to make the results more desirable, to have better strength or hardness, more desirable characteristics. And usually I ask the question, Do you think if we mix these in here, like in this here or this here, do you think it's going to result in a stronger material or a weaker material if we introduce impurities? That's kind of what these are. They're impurities that are mixed in. And normally that's not entirely clear, but as it turns out, alloys are almost always stronger and harder than the pure metals that they're mixing in with. And the reason is because as you mix things in here into these interstitial locations, even the substitutional ones, what happens is it interferes with the slippage planes. So if you've got some more elements in here or in here or in here, or even if you've got a substitutional element, it interferes with the, it's a different type of bonding. You know, the bonds are different in between these elements if you substitute a different element. So either way, it actually interferes with and inhibits the slippage that could occur across slippage planes. And so if it interferes with and makes slippage more difficult across slippage planes, then it's going to make the material stronger and harder. All right. I think I just said most of this. So alloys tend to be stronger and harder than pure materials. So if it's stronger, let's be a little bit more clear. If it's stronger, that means it could withstand a higher force, or if we convert that to stress, stress is force per unit area, it can withstand a higher stress before it gets to the point of plastic deformation. And we're going to call that later on, we're going to call that point the yield strength. We haven't talked about that yet though. And furthermore, if it's more resistant to slippage, if it's stronger, then it can withstand a higher stress before it ultimately fails. And that is referred to as ultimate strength. That's what you looked up in matweb.com for lab 1. Okay, the next topic that's closely related to lattice structures is grain formation. So just briefly, I want to touch on the concept of grains. And this is where I've got a video that I want to show you. But real quick, before I show you the video, if you think about how grains form, all right, so think about a molten metal, really hot liquid metal. And then it's going to start cooling down, all right, after you take it out of the furnace that you're, we'll talk more about different ways to make steel or aluminum later on. But let's just say you take it out of a really hot furnace and it's molten and it's going to start cooling down, all right? What's going to happen is it's going to start to freeze, but freezing doesn't just happen instantly like that for all of the material. What happens is it starts to freeze at certain what are called nucleation sites, or sites where it actually starts to freeze first, and as it freezes, it starts to build up these lattice structures, all right? But it doesn't just, the lattice structures don't just build up from one location. They build up from lots of these initiation or nucleation points in the material, and it grows out from that, and as it's growing out, it's forming this solid lattice structure, and there's lots of these that are kind of growing together all at the same time. And so as they grow together, they form these things called grains. So this is a good picture right here. So these might all be nucleation sites right here, where it's starting to freeze, it's starting to solidify. As it continues to solidify, these nucleation sites continue to add to the lattice structures in their location. But the thing is that they're at random orientations. So the lattice structure here might end up at this orientation, and the lattice structure here next to it might end up at this orientation, and just random orientations of the lattice structures. And so they can't exactly form together into one lattice structure because they're at different orientations. Like you can see here and here and here. They're all different angles. All right, so what happens is they grow together until they can't grow anymore, and we call those grains. and there are grain boundaries where we can identify different grains in the material. And oftentimes you can actually see it to the naked eye, oftentimes, depending on how large the grains are. Here's an example of material. The most common material that I think of when I see these are solar panels, actually. I have some examples in the lab next door of solar panels that are called multi-crystalline solar panels, and they look like this. They have little flecks on them, and those flecks are just differences in the way that these grains are oriented, and their orientation affects the way they reflect light. Right, so that's why they look different. Otherwise, they're made exactly of the same material. All right, and so a material can be made of many, many thousands to millions of individual grains. All right, so with that, I'm going to go ahead and play this video. It's just a couple of minutes, I think maybe 3 or 4 minutes. I will say the video and audio quality is not the best on this video. It's a few years old, but it's pretty good, and it talks about the points that I want you to know. So here we go. I think you can probably see this now. So I'm going to play this.
The safety barriers around this junction are coated with a thin layer of zinc. If we look closely at the surface of the zinc, we see it's built up of many different patches. You can find this effect on a number of zinc-coated objects. The patches you see are crystals or grains of zinc. Here's a piece of a different metal. It's been machined along one edge. You can't see any grains in this surface. However, if we turn it over, it's quite a different story. This piece of metal has been broken in half. Along the broken edge, you can see some of the grains from which this material is made. All metals are made up of grains, although you'll rarely see them like this. In fact, with most metals, including this piece of aluminium, the grains aren't visible, not even on the surface. Here's a way of making them visible. First, we must give the aluminium a mirror-like finish. And there we are. And next we treat the carefully prepared surface with a very powerful acid. Gloves are essential for this operation.
You're basically corroding the metal here. It's called etching, I think he said.
As soon as the acid's had time to react, the metal must be washed. It's then given a second treatment with another special chemical. We call this process etching. The particular chemicals used depend on the metal we're trying to etch. One final wash, and there are the grains. Grains of pure aluminium. They're all similar, both in size and in structure. They appear as different shades only because of the way they reflect the light. By etching, we can reveal the grain structure of any metal. Here's a different sample of aluminium. In this case, the grains are much larger and they vary in size. And here's a piece of copper. In this sample, the grains seem to get smaller as you get nearer the middle. Zinc, a sample whose grains are all shapes and sizes. But how do grains form? To find out, we've gone back to the stage when a metal is molten. In this furnace, the metal is aluminium. When the time is right, the furnace is tapped. The molten metal runs out along channels into molds to form huge slabs of aluminium. In turn, the solid slabs will be rolled into sheets. From time to time, a small sample of the molten aluminium is taken for analysis. The metal is poured into a mold and left to solidify. Now we can see what happens as the aluminium solidifies in a special film. At a number of points in the liquid metal, tiny crystals begin to form and grow.
These are the lattice structures.
Each crystal grows outwards in all directions until it meets the surfaces of its neighboring crystals. In engineering terms, each fully grown crystal is called a grain. In this piece of solid aluminium, there's a very large number of grains.
All right, so that is a little introduction to grains. What are grains? So there's a couple more slides that I want to show. We're almost done. Okay. All right, so we've talked about all of this. As it begins to solidify, then it starts to grow from nucleation sites or inception sites, either thing. They mean the same thing. And the lattice structures start to grow together, and those are individual lattice structures. They grow together until they can't grow anymore because they meet, and we call those grains. And they meet at grain boundaries. And it turns out these grain boundaries are really important in determining the mechanical properties of the materials. That's why we're talking about it right now. All right, so the reason that they are important is because when you have a grain boundary, right, and some of them are at, say, this orientation, and then you have a grain boundary right here, and in this grain next to it, that might be at this orientation. And in the grain up here, it might be at this orientation. So just all different orientations, okay? So the slippage planes are at certain angles in this grain over here. The slippage planes are at certain given angles. You know, they're not all in the same direction. There's some maybe in this direction, and some in this direction, some in this direction. But they're at definite, you know, angles. You can talk about what angles they're at. They're not at every angle, all right? Then in this grain over here, the slippage planes are, say, in this direction, and this direction, and this direction, and likewise up here, they're at different orientations. So the point is that the slippage planes themselves are at different angles and different orientations in different grains, all right? So where you have a grain boundary, that's another place that interferes with the slippage planes, or the slippage of those slippage planes, all right? So in general, the more grain boundaries you have, the more places you'll have that will interfere with the slippage along those slippage planes. So it kind of makes sense that if you have a lot of grains, then you'll have a lot of grain boundaries, and it's going to be a stronger material because it has more slippage planes, and it's going to interfere with the slippage along those slippage planes, all right? And that turns out to be true, and we're going to talk more about this in the heat treatment. But for now, what I want you to know and understand based on what we just talked about is that if you have materials with larger grains, it's going to have fewer grain boundaries, fewer places to interfere with the slippage along slippage planes. And so generally those materials are going to be weaker and softer and more ductile. And the opposite is true for materials with lots of smaller grains. You're going to have more grains per unit volume, more grain boundaries, and therefore those materials are going to be stronger and harder and also more brittle because they won't be able to stretch as much. So there's always trade-offs. All right. And this is the last slide here, just some pictures. Like I said, we're going to talk more about grains and how you can change this. As it turns out, you can actually change this in a given material. I could have a given material, you know, 1060 steel, and I can do heat treatment on that steel, and I can change the way the grains look. I can change the number of the grains, the orientation of the grains, lots of different things about the grains structure. All right, so that's going to be it for this first video. Remember those due dates that we talked about at the beginning of this video for Quiz 2 and Lab 1. Don't forget about those. And in the next video, we're going to talk about the instructions for Lab 2 and how we're going to do that next Tuesday. So I'll see you there.